Hi everybody. We've already talked about the idea that you need a balanced chemical equation for stoichiometry, and in the interest of time, I've actually already written out all of the chemical equations for our practice with mole-to-mole conversions. So what I'd like you to do is pause the video and write us a balanced chemical equation for number 1, 2, and 3 below, and then start the video back up and you'll notice that I am at the same place where you are. Okay, so hopefully you've paused the video. Let me go steal my chemical reaction that I moved out of the way earlier. So here's the chemical reaction for number 1. Again, if you haven't practiced this already, maybe pause the video and try to write this on your own, right? But we are told some information in the problem about carbon dioxide reacting with lithium hydroxide to make lithium carbonate and water. You'll notice I've also balanced it because those pink coefficients are going to be very, very important to us to do stoichiometry. So why is that? What is stoichiometry? Well, actually looking a little bit more in depth at this problem can help us answer that question, and it also brings up a good practice for us to do whenever we're trying these problems. You'll notice as you read the question that there's information about what we're trying to find. It says how many moles of lithium hydroxide are required. And then it also gives us information about what we have when we have 20 moles of carbon dioxide, which we're told, by the way, side note, that's the average amount exhaled by a person, but that doesn't really matter to us. So you should, whenever you see what you're looking for and what you're given, you should write those down beneath the chemical equation. So notice I'm given 20 moles of carbon dioxide. I'm going to write 20 right here, but not just 20, I'm going to write moles because that's the unit that's involved. We won't always be given moles. It asks how many moles of lithium hydroxide are required. So this one is what we're trying to find. And what are we trying to find? How many moles? Now, you might ask yourself, why then do we have this side of the equation? If we only are given information about carbon dioxide and we need information about lithium hydroxide, why even have this whole thing on the right? And the answer to that is that product side is necessary in order to balance our equation, right? So we have to write that out to get those pink coefficients. Without it, we wouldn't know what those pink coefficients should be. Second thing is, the fact that we have information about two different things in this reaction is extremely important. So, what is stoichiometry? If you get nothing else out of this video, this one point will help you out through the entire unit. Stoichiometry is taking information about one thing in a balanced chemical equation, so here we have information about CO2, and giving or converting to information about something else. So stoichiometry, again, we are taking one thing in our chemical equation, in this case CO2, and converting it to something else, in this case LiOH. We actually have the tools to convert to anything else. We could convert to lithium carbonate or water. We can convert from any one thing in a chemical equation to anything else. It doesn't matter if they're on the same side, different side, what have you. But in this question, we are asked to convert between carbon dioxide and lithium hydroxide, so that is what we will do. Now, there's a number we've been given to start with. It's 20 moles of carbon dioxide. Always start with the number. You can't start with an unknown. So we're going to start with that 20 moles of carbon dioxide. Our goal in this problem is to get to lithium hydroxide. But on the way, we know something. We know without a doubt that moles of CO2 must go in the denominator. Why is that? Because we need to cancel it out from up above, right? So we need to cancel out this moles of CO2. That's why it's in the top and the bottom. We are trying to get to moles of lithium hydroxide, moles of LiOH in this problem, right? And we know that because conveniently we've already written it out up here. And so the question is, do we have numbers that allow us to do that? Do we have numbers that allow us to go from moles of one thing to moles of another? Of course we do. It's the coefficients. We know that there's 1 mole of CO2 for every 2 moles of LiOH. Where did those come from? They came directly from the balanced chemical equation. So when you do that math, you'll notice we have 20 times 2. Notice that 20 only has 1 sig fig. That 0 is not significant because it doesn't have a decimal point. So our answer then becomes 40, no decimal point, 40 moles of LiOH, 1 sig fig. We are good to go. All right, let's try another. Again, hopefully you wrote out this equation, but probably what you did not do and what we should do is write out what we are given and what we're trying to find. So it says how many, that's a good indication of what we're looking for, how many moles of ammonia. So we are after how many moles of this. I'm writing down what I'm trying to find and the unit. When we have 6 moles of hydrogen gas reacting. So 6 moles of hydrogen gas, number and unit, are what we are given. And notice again, hallmark of stoichiometry. We're given information about one thing, we're going to find something else. And notice these ones are on opposite sides. It doesn't matter. We can still do the same thing. We're going to start with what we're given, which is 6 moles of H2. Before we do anything else in this question, we might as well write down what we know with certainty, which is that that unit must cancel out. So moles of H2 has to go on the bottom. What are we trying to find? Well, we're trying to find moles of NH3. So let's put that on the top. That's our end goal, moles of NH3. Do we know how to get there? Well, of course we do, because those coefficients we wrote down, those coefficients tell us how many moles of NH3 for every mole of H2. It turns out that there are 3 moles of H2 for every 2 moles of NH3. You'll notice that our moles of H2 will cancel. If you do the multiplication division here, you will be left with 4 moles, because you have 6 times 2 is 12 over 3 is 4. 4 moles of NH3. That has 1 sig fig. We started with 1 sig fig with 6 moles, right? So 6 had 1 sig fig. We end with 1 sig fig. Good to go. Finally, we're going to decompose some potassium chlorate, right? And we are asked how many moles of potassium chlorate. Alert, write it down. How many moles of potassium chlorate are needed to produce 15 moles of oxygen gas? So we're given information about oxygen gas. Some people might get concerned that we're given information about a product and we're trying to get information about a reactant. Doesn't matter. Stoichiometry can convert from anything to anything else in a chemical equation because we're all related by those coefficients. We will simply start with what we know. We know that we have 15 moles of oxygen gas being produced. This, by the way, is the oxidizer that we used for the gummy bear demo that you saw in class. We know that we have moles O2 on top, so we need to do moles of O2 on the bottom so that those units will cancel out. We are ultimately trying to get to moles of KClO3 on top. Do we have numbers that could go in there? Of course we do. We have coefficients. There's a 2 in front of KClO3. There is a 3 in front of O2. So we have 15 times 2 is 30 over 3, but you'll notice that we started with 2 sig figs. So 30 over 3 is 10, but 2 sig figs with 10 can't just be 1, 0, right? Because that's 1 sig fig. 10 with a decimal point gives us our 2 sig figs, and we have moles of KClO3. So hopefully you enjoyed this exploration of converting from moles of one thing to moles of something else. We will need to be very proficient at doing this in order to move on to our next technique, which involves adding grams to the equation.